Welcome to the next session on amplitude modulation. In the last class, we have seen what is double sideband suppressed carrier systems, where we are having three frequency components, out of which we have eliminated the carrier frequency component, and we have two sidebands, the upper sideband and the lower sideband, that is being transmitted along with the transmitter. That's the signal that is being transmitted. So today we will be studying what is single sideband systems. A single sideband amplitude modulated system. A carrier and two sidebands are produced while generating an amplitude modulated signal. And it is not necessary to transmit all these three frequency components. We can reduce the information by using only one sideband alone. That system is called a single sideband system. So it is not necessary to transmit all those signals to provide the receiver with enough information to reconstruct the original signal at the receiver's end. Our objective is that we have to transmit a set of signals, and this particular signal should be reconstructed at the receiver's end without any kind of distortion. That is our only objective. For this objective, we do not need to carry out, transmit all the three frequency components, that is the carrier frequency and the upper and the lower sidebands. In a single sideband AM, the carrier and the unwanted sideband, either of the upper or the lower, either one sideband is removed, and the original carrier frequency, the upper sideband frequency, and the lower sideband frequency are these three frequency components, out of which only either of this lower sideband frequency or the upper sideband frequency is the one that is being used for transmission. So this is an automatic consequence of AM mixing process which we'll have to study. So in order to generate a single sideband AM wave, we have to do some processing with the signal, which we will be seeing as we go ahead. Single sideband AM, there are certain characteristics, certain things that we have to remember, certain points that we have to write. The physical length of the antenna must be equal to the wavelength of the transmitted signal, usually in the radio frequency range. So first point is related to the length of the antenna. So in single sideband systems, the physical length should be equal to the wavelength of the transmitted antenna. The audio signal is too too long to be transmitted directly by a conventional antenna. The audio must be processed by an electronic circuitry. We'll see that what are the electronic circuitry to meet the transmission requirements of the system. This process is known as mixing. That is, the signal that has to be generated after suppressing a carrier and one of the sidebands, we need to do some kind of processing. That is, we will be concentrating on transmission of audio signals. That is, basically we were using amplitude modulation for broadcasting, for radio broadcasting. Previous generation, we had this AM radios, which is now replaced completely by FM radios. The advantages of using single sideband amplitude modulation. We have two major advantages. We have so many advantages. One is that you know that these all things are compared to the conventional amplitude modulation, where you have one frequency component and two sidebands. So once you eliminate all these things, and you say transmit only one particular frequency band, one either lower frequency or the higher frequency, what we are doing is that we are reducing the information to a very great extent so that we save a lot of bandwidth. Similarly, power applications. So single sideband is used to save power in applications where a power saving is warranted. Similarly, we can use when the information is less. Naturally, everything, all the resources can be controlled into a certain way that it can be reduced to a great extent. So let's draw the block diagram of an SSB transmitter. We have three methods of generation of AM signal, single sideband signals. The first one is known as the balance or the filter method, balance modulator method, or the filter method. The second method is known as the phase shift method. And the third method is something new that's called as third method itself. So this is a block diagram for a balance modulator method. block diagram for a filter method of sideband suppression. We have a crystal oscillator here to generate the carrier wave signal. After that, we have the input here, audio frequency input. The carrier wave is after buffer is given to a balanced modulator, and we have an audio amplifier here, and we are giving the audio input where the balanced modulator creates a DSB-SC system here, DSB, double sideband and suppressed carrier, where the carrier frequency component is suppressed. And then we have a sideband suppression filter, and we'll filter the other band. So we'll have a single sideband system, after which we have a crystal oscillator to increase the frequency, and then we have a balance mixer, and then we have SSB output to the linear amplifiers, from where it is given to the RF antenna for transmission. So a balance modulator, we'll see how we are going to explain this block diagram and what are the other features of the balance modulator filter method. A balanced modulator is a circuit that multiplies two signals. We have already seen that to generate a DSB-SC signal, what we do is that we multiply M of t with C of t. So here a balanced modulator is a circuit that multiplies both the signals while cancelling the feed through of one or both of these signals. The output of a balanced modulator is a DSB-SC signal. Filters are used to remove the unwanted sidebands. After DSB-SC signal, that is, after suppressing the carrier frequency components, what we are doing is that we are filtering out using a band pass filter, either at the upper or the lower frequency sideband. The balance modulator filter method, the next point is that the key circuits in this transmitter are the balance modulator and the sideband suppression filter. So what a filter is a band pass filter with a sharp cutoff at each side to obtain adjacent sideband rejection. So we have a particular set of, this is called as a band pass filter, where this is the upper cutoff frequency FU and FL. So a band pass filter allows only the frequency components which is in between the upper and the lower cutoff limit of a upper and lower cutoff frequency limits, and we need an adjacent, we need a very sharp sideband rejection, so that we have a high attenuation outside the band pass. That is, any signal that is being outside the frequency component of the either FC or the upper or the lower limits, it should not be allowed to pass through this filter. So let us mathematically write the equations for the balanced modulator. So let us consider the output from the balanced modulator to be ET of t cos omega c t, where EM is the message signal, cos omega c t is the frequency component of the carrier signal. K is a multiplier constant, and with the cosinusoidal input of EM of t is equal to EM max, that is the maximum. EM max cos omega ct, the modulator output becomes a DSB-SC signal containing only two side frequency components. E of t is equal to K EM max cos omega mt cos omega ct. So using the trigonometric relation cos A cos B, that is cos A minus B plus cos A plus B, we will get E of t is equal to EM cos omega c minus omega m of t plus omega c plus omega m t. You get the additional and subtraction components, and E max here, this EM max by 2 into K. So we make it into a single constant term which is called as E max. Is that clear? So these are the carrier frequency components. This is the first one. We have conventional AM modulated signal with the carrier frequency component and the upper sideband and the lower sideband component, FC minus FM, FC plus FM. Then we have this is DSB SC systems, suppressed carrier, where you don't have the carrier. This A is the conventional DSB, SC system. B is A is a conventional amplitude modulated system. B is DSP suppressed carrier system. C and D are the single sideband SSB systems, where C is the upper sideband and the D is the lower sideband. So these are the frequency components in amplitude modulated signal. Now, one of the side frequencies in DSP-SC is removed, and either it is the upper side frequency. Here, let us calculate the upper that is EUSF. That is the output. Upper sideband frequency is equal to E max cos omega CT plus omega MT. Similarly, the lower sideband, it will be omega C minus omega MT. The overall power transmitted is given by PT is equal to E max square by 2R. Now let us consider a DSP-SB modulated using sinusoidal waveform. Let us consider the message signal M of t. The signal that you are going to modulate, M of t is equal to AM cos 2 pi FMT. And the carrier signal C of t is equal to AC cos 2 pi FCT. In that case, the single sideband, that is the double sideband, both the sidebands, a signal at DSB-T is given by C of t into M of t. Multiplying these two things, we'll get ACAM cos 2 pi FCT cos 2 pi FMT. Using the trigonometric relations cos A, cos B, cos A, cos B is equal to 1 by 2 cos A plus B plus cos A minus B. So we'll get two components here, 1 by 2 AM, AC AM cos 2 pi FC plus FM, FC minus FM, this upper sideband and the lower sideband. The signal at the output SUSSB, where U stands for the upper sideband. S is the signal at the upper sideband, USSB, upper single sideband of T will be the plus component here, FC plus FM, 1 by 2 ACAM cos 2 pi FC plus FM of T. Then upper sideband, now you again using the trigonometric cos A plus B, cos A, cos A B minus cos A cos B minus cos sin A sin B. So using the trigonometric relation, we'll get AC AM cos 2 pi FCT 2 pi FMT minus 1 by 2 AC AM sin 2 pi FCT plus 2 pi FMT. This is the upper side. Similarly, next slide we'll see what is the equation for the signal at the lower sideband. Here it is plus, in the previous lower it was minus. The same way we have two sign components. That's it. Cos A minus cos B. There it was cos A plus cos B. So with this we have studied the first method, balanced modulator method of generating a single sideband system. In this, we have derived the equation for the signal at the output for a single sideband system, where we have used both the single signal for the upper single sideband and the lower single sideband system. Thank you all. Thank you very much for listening to this session. The next class, we'll see the phase method for generating single sideband carriers. Thank you all. Thank you very much for listening.